Today we're going to be talking about a process known as combustion analysis, which allows us to calculate the empirical and molecular formula of an unknown chemical compound. Just a quick rundown of the objectives in this video. We're going to start by reviewing percent composition from previous videos. The calculations we're going to do in this video are basically the opposite of a percent composition calculation. In percent composition, we go from formula to percentages. In these calculations, we're going to go from percentages back to formulas. Once we got that review under our belts, we're going to start talking about some definitions of some key terms that are going along with this section. We'll then talk about combustion analysis itself. I'll discuss the device and how it works. You can see we have actually a quick diagram of a lab grade version of that over to the right. And we'll also talk about what kind of results this machine gives for you. Lastly, we'll take those results and we'll determine how we can figure out the empirical formula of a chemical compound and ultimately the more useful answer, which is the molecular formula of that chemical compound. This will be a series of calculations and we'll have plenty of practice towards the end of the video. To start, let's go over what again percent composition means. We're basically discussing the mass fraction of each individual element in a compound that is represented as a percentage of the total mass, which is the molar mass of the compound. So really what we're getting into is what fraction of that total mass of the compound is made up of each of the individual elements, and we represent that as a percentage. If this is something that's new to you, you should stop the video now, go back and watch the video on percent composition, and then come back and give this a try in a moment. A quick example of what we're talking about, we have the chemical compound copper sulfates listed right over here. And through some simple calculations that you should already be comfortable with, we can determine that the copper sulfate is 39.8% copper, 20.1% sulfur, and 40.1% oxygen. And that's a fraction of the total weight of the entire weight of the compound as a whole. Again, if you're not sure where these numbers came from, please make sure you go back and review the video on percent composition. As I mentioned earlier, our goal today is to go back with these percentages and then use them to go back and identify a chemical formula. This combustion analysis process will give us this data, and then we have to go back and figure out what chemical this data actually came from as a way of identifying unknown substances. So let's get into the actual process itself. This is the process known as combustion analysis. This is a lab process you can use, and it's used to identify unknown chemicals by burning them and collecting the products of that combustion process. So that's what we're going to do. We're going to burn these things and collect the products. The combustion process itself separates the compounds into their separate individual elements. If you recall from previous discussions, we just talked about a combustion reaction. So for example, we can have a compound made of A, B, C, and D, 4 individual elements bonded together. Combustion means we will react this compound with oxygen gas, and when this reaction occurs, what we're going to get is oxides of each of the individual elements. By separating the elements like this, combustion analysis allows us to analyze and collect each element separately, which eventually will relate back to how much of each of those elements must have existed in the original compound. So again, this combustion process separates those elements into different components. Because of conservation of matter, after looking at that previous reaction, we can say that the mass of those individual things we collected, the AO, the BO, the CO, etc., must relate back to the mass of the individual element from the original unknown that we had. So the amount of AO that we can produce must be related to the amount of A that was originally in that unknown. And this again is how we get back to those ideas of percentages. This process is cheap, it's fast, I said inexpensive. We already talked about that. But unfortunately, it has a bad side to it. This process is destructive, meaning to actually run the test, we have to destroy our sample. If your sample is valuable, if your sample is rare, or if your sample simply doesn't burn, this is probably not the best process to use. However, if those things aren't an issue, this is a really quick and easy way to get some good information about what the chemical formula of your unknown substance actually is. Before we actually talk about the process itself, here's a couple quick pictures of what these devices might actually look like. On the left, we have a picture of a lab-sized piece of equipment. The way this works is you would inject a sample up here on the top. The combustion process would happen somewhere in the machine, and then each of these little tubes here are removable, and they would collect one of the individual products from the actual process. We could get masses of those, and as you'll see in a minute, those masses would allow us to calculate the formula of our substance. Likewise, these are similar devices. that are more portable. These are something you would bring to a site in order to detect certain chemicals. The combustion process does not actually occur inside the device, but this device can take in the products of a combustion reaction and then analyze them to figure out what fraction of each element must be present. A lot of times these are used in the detection of what are known as volatile chemicals or combustion products. For example, at an airport, if they're trying to detect something dangerous, something flammable you might be bringing on a plane, this could be a device that we could use to do that kind of a detection. Now let's get into the actual process of how this thing works. We have here kind of a cartoon drawing of what a device would look like on the inside, and there's a couple phases to the process. So you start over here on the left with a container, usually made of steel, something that's very temperature resistant, and this is basically a furnace. You would put your unknown sample, and that's the thing we want to note here. We don't know what this stuff is. You'd put it in a container or a dish inside of here. We would apply a significant amount of heat to this process, and we would also provide a supply of oxygen gas. The oxygen gas would come in, it would mix with your substance, and the heat would cause this stuff to burn. And when it burns, it's going to create all of those oxide products that we talked from before. Those oxide products would then get carried down the pipe due to the flow of oxygen towards what these guys are. These things are known as traps. These two containers here are known as traps. And the goal of the trap is to catch the individual products that were created. For example, in this first trap, we are catching the trap contains, magnesium perchlorate. The purpose of having this magnesium perchlorate is that magnesium perchlorate reacts specifically with H2O, and that H2O that's going to pass over here is going to get stuck to the magnesium perchlorate molecules that are in here, and it's going to get trapped. The other chemical products of this reaction aren't. Those guys are going to pass clear through because they don't react with magnesium perchlorate. Those other products, in this case they're going to be carbon dioxide, are going to travel into the next trap, and they're going to get stuck to this. Sodium hydroxide specifically reacts with the carbon dioxide gas, and the CO2 gets stuck here, and all that carbon dioxide we produce gets stuck in the trap. So this guy specifically traps the water, this guy specifically traps the carbon dioxide, and then hypothetically by the time you're done, there should be nothing left coming out of the end of your device here. If your compound contained more stuff, we would have to have more traps to catch the individual elements. But let's talk a little bit more about that trapping process. Let's have an example here. Say, for example, we were doing a test where we were running a sample on some compound that contained an unknown number of hydrogen and carbon atoms. We would react that with the oxygen. That's what happens right here in the combustion chamber. And that would create products. The products, again, are the individual elements combined with oxygen. One of those products would be carbon dioxide, and the other, which is the carbon oxide. The other one would be dihydrogen monoxide, which is water, and that's the hydrogen oxide. All of the carbon dioxide that was produced in our reaction would get trapped here. All of the water that was produced in our reaction would get trapped up here. Now, the reason we do this, what we're really interested in here, is the mass of the traps that actually happen here. So, for example, in this trap right here, with the magnesium perchlorate, all of the H2O that was produced gets trapped in here. What we can do is we can record the mass of each trap before and after. What this will get for us is the mass, for example, of H2O that's collected. What's important to remember in this process is that the mass of H2O collected is dependent on the mass of hydrogen that we originally started with, and that mass of hydrogen, the only source of hydrogen, was the original sample that we had. So this is the only source of the hydrogen atoms that happen in this process. So the amount of water we create is determined by how many hydrogen atoms were originally here. Let's write that down. So the amount of H2O formed is dependent on the amount of hydrogen in our unknown. If there's more hydrogen in the unknown, we would expect to create more water. So we can calculate this mass of H2O collected, and then ultimately that mass of H2O relates back to the mass of hydrogen in your sample. If you know the mass of the hydrogen in your sample, we can take that, divide it by the total mass of the sample, and ultimately what this leads to is an information about the percent hydrogen in the original sample that you started with. You would likewise repeat that process with carbon dioxide, and that would get you information on the percent carbon in the original sample. From that percentage data, we can then go on and calculate things like formulas, which we're going to talk about next. But just in summary, when we're talking about the combustion analysis device, we burn the sample in here. It creates individual oxide products of the individual elements. Those individual oxides are collected in individual traps, which are then masked. The amount of mass of material collected in the trap corresponds back to the amount of mass of the original atom that must have come from the sample. And this allows us to figure out the percent of each element that must have originally existed back here. Once you've done all this work, you're going to get results from this combustion analysis process, and those results can come in two different forms. First of all, I can provide for you the percent composition data. So I can say that your substance is 36.1% carbon and 43.8% oxygen, et cetera, et cetera, et cetera. And I'll tell you all those percentages. We'll go through some problems together that has you figure out to take these percentages, and ultimately, again, our job is to get back to a formula. Some formula CX, OY, where we figure out the values of X and Y. Likewise, what I can also give you is the mass of each element from the reaction. So I can say that you have 2.81 grams of carbon and 4.56 grams of oxygen. Even though that's different data, we're still going to want to go back and come up with some formula where we figure out the values of X and Y that would tell us how many carbons and how many oxygens. The good news is the process is very similar for both. This guy has a little bit of an extra step. This guy's a little bit shorter, but both of them are very similar in mathematics. Now, before we dive into the actual calculations itself, it's important to differentiate between the kinds of answers that we can get. And there are two types of formulas that we can create from this process. The first one we'll talk about is something known as an empirical formula. The empirical formula is simply the smallest whole number ratio of atoms in a chemical compound. It's not necessarily the actual formula, and the key word here you want to focus on is it's just the ratio. For example, if we had the compound H2O2, its empirical formula would just be this, HO, a 1-to-1 ratio of hydrogen to oxygen. That's not really what the formula is. H2O2 is hydrogen peroxide, but the empirical formula of it is HO. As you might imagine, empirical formulas are not as useful for us as what we're going to talk about in a second, but these guys, the important thing to note, empirical formula is the results of our combustion analysis calculations. So this is what we get when we do combustion analysis. We just get the empirical formula. There's actually some extra steps to allow us to get the next part, which is the molecular formula. In a molecular formula, we identify the actual number of atoms in each compound, meaning it's not just a ratio. It tells us there are this many atoms and there are that many atoms of the other substance. It's important to note that your molecular formula should have the same exact ratio as your empirical formula. So again, whereas HO would be the empirical formula of this, the molecular formula of this compound would be the H2O2. There's 2 hydrogens and 2 oxygens, even though their ratio only boils down to 1-to-1. This, typically, is the formula that we're interested in. This is the one we want, but unfortunately, we have to get this guy first and then translate our empirical formula into our molecular formula. And again, we'll go through that with some examples. At this stage in the process, we're actually going to go through a couple examples here. And the first one I'd like to try is the example that we had right back from the beginning of our video. The combustion analysis equipment would spit out this information. It would tell us that our sample is 39.8% copper, 20.1% sulfur, and 40.1% oxygen. We're looking for a formula that's going to look like this. We got to figure out the numbers X, Y, and Z that would tell us how many coppers, how many sulfurs, and how many oxygens. What I like to do first to start this process out is to list out the information that's given over here. So we're going to have 39.8% copper, we're going to have 20.1% sulfur, and we're going to have 40.1% oxygen. First things first, when we want to come up with our formula has, as I said before, Cu, S, and O. X, Y, and Z are in numbers of molecules. But as we've talked about a lot recently, we don't typically like to keep track of number of molecules. This is really number of moles. If we can keep track of number of molecules, we can keep track of them in terms of numbers of moles. So we got to find mole values for how many moles of copper versus how many moles of sulfur versus how many moles of oxygen we're dealing with here, and that'll allow us then to plug numbers into this formula. Well, to start with, we have percent data, and then ultimately we want to get over here to mole data. Well, the thing to remember is that these guys are actually percentages of mass. So these are actually mass percentages. And there's a couple ways we can get rid of this percent sign, because again, eventually we want to get to moles, and we can't get to moles from percentages, but we can get to moles from mass. So one of the things we can do is a couple ways to handle this. I think the easiest way to handle this is we're going to assume a 100 gram sample. The sample may not have originally been 100 grams, but that's not a big deal. This is a ratio, and as long as it's the ratio of the same original starting value, the ratio itself won't be affected. The reason we choose 100 grams is because it makes our life very easy. This now becomes 39.8 grams of copper. This becomes 20.1 grams of sulfur, and this becomes 40.1 grams of oxygen. So now we've gotten rid of percentages, and now we're in terms of how many grams we have. But again, to write a formula is a ratio of moles, not a ratio of grams, so we've got to do another conversion. Well, this one should be a little more obvious. We want to convert each of these from grams of the individual element into moles, and that's going to require us to do some of the mole conversions we've already worked on. We need to look up the molar mass of each compound and then use that to do the conversion. I strongly recommend when you look these up that you use as many decimal places as possible, because rounding can be a little tricky in these problems. So looking up our elements, we find out that copper is 63.546 grams for every 1 mole of copper. Sulfur is 32.065 grams for every 1 mole of sulfur, and oxygen is 15.9994 grams for every 1 mole of oxygen. We can take a minute, do those quick calculations. I recommend pausing the video and doing them on your own, and then we'll talk about what we can do with the answers and how that's going to get us to our formula. So now that we've done a little bit of mathematics here, we've converted these 3 gram values into moles, and we get 0.626 moles of copper, 0.627 moles of sulfur, and 2.51 moles of the oxygen. Now, unfortunately, again, the goal here is to come up with a formula, to come up with these values for x, y, and z for this substance. Unfortunately, these are not whole numbers, and we need whole numbers to plug in here. You've never seen a formula with a decimal in it. So we got to use a little mathematical trick to convert these into whole numbers. We want to keep the ratio the same. If we multiply or divide all of these by the same constant value, that'll maintain that ratio. The best thing you can do is take each one of these answers and divide them by whatever value is the smallest. That will guarantee that at least one of these values comes out to be a whole number, and you're going to hope that the rest of them do as well. 0.626. And when you do the math to calculate these, the first one's going to come out to 1, which means 1 copper atom. The second one is also going to come out to 1, which means 1 sulfur atom. And this last answer here, when you do your math, is going to come out to 4, which means 4 oxygen atoms. And those do come out to nice rounded whole numbers, plus or minus a couple hundredths, and that's exactly what you're looking for. Put all of this together, and we get the formula that looks like this: CuSO4. And if you recall from earlier in the video, that's exactly the formula we started with. So we're able to go from the percentages over here and eventually translate it from percentages to grams. We were then able to go from grams to moles, and then finally we were able to go from moles to a reduced answer, and we get this formula right here in terms of copper sulfate. We're going to try a couple more of these, but you're going to find that the process is always the same, and I'll try at the end of the video to come up with a list of instructions, a step-by-step process that allows you to tackle these. And I think once you've done a bunch of them, you'll find that they get very repetitive and ultimately relatively simple. Now let's take a look at a second problem together. In this situation, we have a similar setup. In this case, we have 61% carbon, 15.3% hydrogen, and 23.7% nitrogen. Just like before, you want to go from the percentages to grams, assuming a 100 gram sample. You then want to go from grams to moles, and then finally you want to take that answer and you want to reduce it. What I'm going to allow you guys to do at this stage in the game is to take a minute, try this problem on your own, and then we'll go through the answer together to make sure that you're getting correct work. All right, let's see if we can't go through the work for this particular problem. As in the previous one, we're going to start by translating these. We're going to have 61.0% carbon. We're going to have 15.3% hydrogen, and we're going to have 23.7% nitrogen. Do yourself a favor, leave yourself a little space between each one. It's going to allow you to do a little bit of work. Again, we're going to assume 100-gram samples, and that allows us to do this. We go from 61%. 61.0% of 100 grams is 61 grams. Nice and easy. Likewise, we get 15.3 grams of hydrogen, and we get 23.7 grams of nitrogen. So that gets us from our percentages to our grams. If you recall, our next step is to get grams into moles, because that's what's going to get us the formula that goes along with these three elements. We'll put in a multiplication sign and a line for each one of them. You have to look up these masses on your periodic table. Turns out that there are 12.0107 grams for every 1 mole of carbon. There are 1.00794 grams for every 1 mole of hydrogen. And there are 14.0067 grams for every 1 mole of nitrogen. Plug all this stuff into your calculator and we'll get 3 answers. I believe from my work I got 5.08 moles for carbon. I got 15.18 moles for hydrogen, and I get 1.69 moles for nitrogen. This is a ratio of moles, meaning we could plug these in for X, Y, and Z, but we'd rather see these numbers as whole numbers. If you recall, we talked about a mathematical trick for doing this. We can take all of these and divide them by the smallest value. That's going to guarantee that we get at least one whole number, and we're going to hope the others work out as well. So 1.69 divided by 1.69 gets us 1. Nice and easy. 15.18 divided by 1.69 is going to get us the answer of approximately 9. It's not perfect, but your answer should always be within a couple hundredths. And again, 5.08 divided by 1.69 also gets us very close to a whole number. In this case, we're going to get the number 3. So we get 3, 9, and 1, everybody's whole numbers, which means we can now write the formula for this compound as being C3H9N. 3 carbons, 9 hydrogens, 1 nitrogen. And that is the formula now that corresponds to these weight percents of our 3 elements. Let's do one more example. This one works exactly the same as the last two, except we're going to roll in the second part of this process, which is going to involve calculating molecular formulas. And this is something we'll develop further while working in class. Again, pause the video, take a minute or two, see if you can calculate the formula for this compound, and then we'll talk about how to get the second part, which is the molecular formula from our empirical. All right, let's start talking about the answer for this process. As you do more and more of these, you're going to find that you can streamline this a little bit. For example, one thing to make your life a little easier is to do this, 6.0 grams of hydrogen. No reason to write those percents again. 94.1 grams of oxygen. We've gotten from percents into grams. Now we want to do the next step, which is converting into moles. Hydrogen is 1.00794 grams for every 1 mole. We look this up off our periodic table. And then oxygen is 15.9994 grams for every 1 mole, again from our periodic table. Plug this all into your calculator, and we end up finding we get the answer 5.95, and we get the answer here of 5.88. Divide everything by the smallest, 5.88 and 5.88. This definitely comes out to 1, and this pretty much comes out to 1. I think you get like 1.02 here. Both of those are very close to the value, in which case we get an empirical formula. And what this tells us then is that our empirical formula, our ratio, is a 1-to-1 ratio. And if we recall back from the beginning, we identified this term, empirical formula. So we get this formula HO. Unfortunately, this is not the formula for the actual compound. This is just the ratio of hydrogen to atom, or hydrogen to oxygen atoms. This means we have a second step in this process. Typically with these problems, you're going to get a second bit of information that's going to look like this. We're going to use a second piece of equipment in the lab known as a mass spectrometer, and it does exactly what it sounds like. It measures the mass of your actual sample. And it's going to tell us that the molar mass of our real compound is 34.015 grams per mole. Well, if the formula we found, which is HO, is the right formula, then its molar mass should match the molar mass of the given compound. So that requires us to calculate this. The mass of a hydrogen atom is somewhere in the vicinity of 1.00794. The oxygen atom is 15.9994. There's one of each of them, so we're going to take these two numbers and add them together. And when I do that math, I get an answer of something in the vicinity of 17.0073 grams per mole. And what you'll notice is that these two numbers here do not match one another. The mass of the atom, the molecule we calculated, does not match the molecule that was measured via our mass spectrometer. That doesn't mean that this is wrong. That just simply means that this is a ratio only, and it's not the actual molecular formula for our compound. What you might notice from these two masses is that they are related to one another. 17.073 is just about half of 34.015. And in fact, if we take 17.073 and we double it, we get the answer. So if we do this times 2, we get the answer of 34.015, which is exactly the same in this case as the one we have here. Well, if doubling the mass got our molecular weights, or our molar masses to match, then we can do the exact same thing up here to the formula. And it turns out that the real formula of this compound isn't HO, but it's actually H2O2. And this, as I said before, would be the molecular. The molecular formula, that's not even close to right, of the compound, and this is what we'll ultimately be looking to get. So the math we've done earlier calculates what's known as the empirical. The math we just talked about with our molecular weights or our molar masses is going to calculate for us a molecular formula. Both of these are part of the answer, but ultimately it's this guy down here that we're really going to want. To wrap things up, I think it's important to have maybe a summary of the entire process here. Depending on what data you start with, this is the process you'll use to kind of get from the beginning information, those percentages, all the way to a molecular formula. I very strongly recommend you write this down somewhere as a couple steps. There are plenty of practice problems online for you to try, and this would allow you to kind of gain some experience with this. The first couple times through, use the process as steps, but you'll find very after that this is very formulaic, very procedural, and it's something you can do over and over again and start to get into your mind. So like I said, copy the steps down, try a few more problems. We'll tackle some scenarios in class tomorrow where this starts to get a little bit more complicated.